In 1997, the world awakes to a comet secretly entering our solar system. Two amateur astronomers spot an unknown intruder near Jupiter, more brilliant than any they've seen before. Dubbed Hale-Bopp after its discoverers, it was a visitor from the Oort cloud on its first journey around the sun in almost 5,000 years. The comets we most often see are little more than asteroids. Their gas and loose dust burned off in their frequent jogs around the sun. But comets like Hale-Bopp, just out of the Oort cloud's deep freeze, have plenty of ice and dust to shed.
They've got water ice, they've got carbon dioxide ice, dry ice, they've got carbon monoxide ice, and all of these ices are much more volatile than water. So when they get in the inner solar system, they go nuts.
Fortunately, we could marvel without fear at Hale-Bopp's glorious moment in the sun. It sailed by unobstructed, 200 million kilometers from Earth, just a bit further away than our sun. But what if it had been on a collision course with our planet? In 1992, the US government launched an aggressive program to analyze the threat comets and asteroids pose to Earth. It's called the Space Guard Survey. Today, scientists all over the world are involved in the painstaking process. They point their telescopes at a single region of the sky and take periodic snapshots. Then they line up the images, looking for anything that moves from frame to frame.
We are looking first for the larger asteroids and comets, the ones a mile or so in diameter, and eventually we'll extend it to the smaller ones.
Scientists estimate that our solar system has about 1,100 comets and asteroids that are a kilometer in diameter. So far, searchers have identified over 700 of them. And those are just the giants that could do apocalyptic damage. We may never be able to locate every threat. There could be millions of comets and asteroids that measure 100 meters or so, the length of a sports field. That's more than 3 times the size of the rock that slammed into Arizona 50,000 years ago. Still, telescopes are a first line of defense against what could be a major disaster for our planet.
If you don't look, you won't know anything's coming. We would be taken by surprise just as much as the dinosaurs. If you do carry out a survey, then you hope that you can have warning. But it's one or the other. Either you have years or decades of warning, or you're taken completely by surprise. There's nothing in between.
There's 3 things that are important. You have to find them early, you have to find them early, and you have to find them early.
Suppose we do detect a comet headed for Earth. Then what can we do? Scientists have just started to come up with solutions. One of the leading ideas, smash a rocket into it to slow it or knock it off course. That's harder than it may seem. If comets were hard ice balls, as first thought, a powerful thump from a rocket might do the trick. But some comets may be porous. They could just absorb whatever we throw at them, like a sponge. In 2005, scientists were ready to test their theories about how a comet would react when it was hit. They were going to try to crash a rocket into one. They call it deep impact. They're going to see what happens when a spacecraft slams violently into a comet at 37,000 kilometers an hour. Deep Impact's primary goal is to peer inside a comet. That inner material has remained relatively unchanged since the solar system was formed and could provide clues about the solar system's beginnings. But astronomers also hope to gather ideas about how to stop a comet heading toward us. Deep Impact began here at NASA's Vertical Gun Range in Mountain View, California, where it was the job of Dr. Pete Schultz and his team to figure out what the comet would do when it was hit.
This particular instrument allows us to fire a small sphere, about a quarter inch, at speeds that are maybe 6 or 7 times the speed of a rifle bullet. This whole assembly rotates up to an elevation where the gun is basically 3 stories high. This allows us to send a projectile through different openings in the chamber so that we can impact a flat surface at different angles.
Scientists believe comets vary in their makeup, so Schultz and his team built several different models, then hit each with shot from their ultra-high-speed gun.
The first scenario is what happens if we impact into something that looks like lunar dust. The second one is what happens if we impact into fluff. And the third one is what happens if we impact into a fluff covered with an organic layer. As we go down and look at the evolution of this crater, we find at the very end, after it's finished, we can still see the crater here. But in these 2 cases, when we're using fluff, we can't see the crater. It's completely masked.
The fluff completely absorbed the projectile, a frustrating result for scientists hoping to get a look inside. And there was another possibility Schultz had to consider. What if the entire comet is extremely fragile and porous? He searched for a substance for that simulation.
The comet may be sort of like a fluff ball. It may have been very low density. What do we do to try to simulate that? The best thing probably is a complex organic. What would that be? Cotton candy. So what we're going to try to do is to concoct a superficial comet, an imaginary comet, and see if we can't fire into that and see what happens. So what we'll end up doing here is to get this very low density, this fibrous material. Okay, that looks pretty good. Okay, what we're now going to do is we're going to suspend this in the vacuum chamber, slam into it at very high velocity, and we're going to find out whether it blows it apart or if the projectile will go straight through. Okay, we're all set. We've got our comet made of cotton candy. Let's turn off the lights and let's get out of here.
The projectile soars right through the comet,
Can you back her up?
but the force shatters it.
Oh, is that cool? Kapow! Well, it did drill through it.
Yeah.
Gosh. Okay, I gotta see this. Oh my God. There's no more comet, that's for sure. What a mess.
But this is not good news. A shattered comet can be even more dangerous than an intact one. The pieces tend to remain on the same path, turning one projectile into many. In 2005, once the team completes their tests, NASA is ready to take the plunge. It will try to drive a 370-kilogram impactor into a comet to find out what's inside. Deep Impact's principal investigator is the University of Maryland's Dr. Michael Ahern.
So here we have the model of both Deep Impact spacecraft. Many people think it was only one spacecraft, but it's really 2. The flyby spacecraft has all the instruments on this platform on one side, and if I turn it around, these are the solar panels that provide the electric power. Here's the impactor. That is a 1/3 of a ton geologist's hammer with which you hit something to see how it behaves when you hit it.
January 12, 2005. After 6 years of study and preparation, Deep Impact is ready for liftoff.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Deep Impact.
The spacecraft's destination is a 6-kilometer-wide comet named Tempel 1. Discovered in 1867, it's well known to astronomers. It orbits the Sun every 5.5 years and has lost much of its gas and ice.
People would argue that you should preserve the comets for posterity, but doing a violent study on one that is just typical of a whole class seemed to us to be the right choice for science.
Deep Impact takes just 5 months to reach Tempel 1's orbit. On July 4th, 2005, it turns and points its cameras at the comet, 860,000 kilometers away. Then it releases its impactor. If all goes well, the collision will blow a hole in Tempel 1 about 200 meters across and 8 stories deep, about the size of the Roman Colosseum. But it might destroy the comet by breaking it apart.
I was more worried that we didn't know enough about the comet and the impactor might go in and just make a meter diameter hole 100 feet deep. And then we'd be hard-pressed to tell whether we had actually hit or had missed.
Back on Earth, hundreds of scientists hold their breath.
We lost signal, and we had to stand there and wait around. So everybody was trying to be, go keep busy and not feel anxious.
But just in time, the signal returns.
Yes.
The energy went in, bounced back, and drew out all this material from beneath the surface, which was then exposed out in space into sunlight. And so this is scattered sunlight off of all of this debris that was excavated from the interior of Comet Tempel 1.
The 6-kilometer-wide comet and NASA's 370-kilogram craft have collided at 37,000 kilometers an hour. The explosion is equal to nearly 5 tons of TNT. It completely vaporizes the impactor, and it kicks up far more dust than anyone expects.
One of the reasons it was so dusty is that the particles were much smaller than we thought. This is a very fluffy body.
The amount of dust is a telltale clue to the comet's makeup. Tempel 1, at least on the surface, contains far less ice than scientists expected.
There was no way that there were large blocks of ice anywhere or rock. And that really is helping us formulate how did these comets get put together? How did they break up? This is the first data we've ever had. So in that sense, it's revolutionary.
Analysis of the dust showed molecules containing carbon, organic material. So it's plausible that comets could have brought such material to Earth early in its history. A return mission is planned to take another look.
In 2010, NASA will have redirected the Stardust spacecraft to go back to Tempel 1 and look for the crater that we formed to see what happened to the surface and the rest of the comet when we impacted it.